So now we are going to look into the P-type 2D FETs, and so N-type 2D FETs are pretty mature. We have been working on N-type 2D FETs for the last 13 years. P-type is not as mature. I mean, people are very recently getting interested in P-type 2D materials. So it will not be as elaborate as the N-type discussion. And what I told you is that making N-type 2D FET is easier because the Fermi level of the metal, the pinning, happens close to the conduction band. Okay, so therefore, if you just tune the Fermi level little bit here and there, even with the known metals like antimony, bismuth, I could get into the conduction band, and I can make a good N-type contact. It's very forgiving. So most of the 2D materials are very forgiving in terms of the N-type, and MOS2 and WS2 are prime examples. Okay, but if you go to, because you see the Schottky barrier height is kind of small, right? It's not very large, right? While the Schottky barrier height for the P is very large, because the sum of the two is the band gap, right? And the band gap of MOS2 is 1.8 eV. So if you have a small Schottky barrier height of like 0.1 eV for the electron injection, the Schottky barrier height for the holes are 1.7, right? So it's very difficult to inject holes, and when you apply bias or dope it, you kind of make this Schottky barrier even thinner. You see, now you can tunnel through. Right? This is what we spoke about, right? And that's how you get to a good contact at the end of the day, right? But this is not allowable for the materials which are showing more intrinsic P-type characteristics like molyselenide or tungsten selenide. Okay? These materials, the problem is the Fermi level is pinned mid gap. It was almost like ना घर का ना घट का, ठीक है? मतलब यहाँ पे तो N type हो गया, यहाँ पे अगर इस तरफ होता, right, then I would have been benefiting, right? But the problem is it is mid gap. So no matter what metal you choose, it will all be over here, right? And what is the band gap? 1.8 eV. If half of that is 0.9 eV, that's a huge Schottky barrier. You see, so huge problem in getting high performance P-type FETs or low contact resistance, right? That's a fundamental problem with P-type 2D FETs, right? Which is not as much there with N-type. Okay? So as I know that I mean, if we can thin it down, okay, we'll get it better. But still, I mean, we really have to thin it quite a bit, because higher the barrier height, more thinner you have to make it. That is simple quantum mechanics, right? The barrier width and barrier height both has to go down. If you cannot go down on one, the other has to be even further reduced. Okay? So therefore, and this problem is mitigated in silicon, as I told you, through degenerate doping, because of the fact that in degenerate doping, right, you use a P++ contact, and you make the channel intrinsic or N-type or whatever it is, and that's how you get to very thin Schottky barrier width. And this is again kind of going back to the same formula that we discussed in the previous lecture by degenerately doping. So ND has to be very large, then I have a good contact. So the question is now, how do we do it for P-type 2D FET? So let's see. So then we search for the P-type dopant. Okay, so you can do some DFT calculations and look into because you have to do substitutional doping, right? For example, for silicon, what is a P-type dopant? You guys know? What element of the periodic table should I choose for P-type doping? No, carbon you never use. Carbon you never use, right? So similarly, we have to find another transition metal which can replace tungsten and give me P-type doping. And if you do a lot of DFT calculation, you will find that tantalum, vanadium, niobium, these are good P-type dopant for most of the 2D materials. Okay. So what we did is, these are a lot of characterization, don't have to worry about that. So we have a collaborator in Prague in Czech Republic, okay, a wonderful place. I like to have collaborators in those places because I get to go to all these wonderful places and hang around and then send the samples. Students are working in the lab, I am roaming around and enjoying my life. Okay, so these are the crystals that we get which are doped with niobium, vanadium and tantalum. So this is how these are like crystals. And this is grown using something called the chemical vapor transport. Okay, it's a CVT growth process. This is not CVD, not MOCVD. These are like crystal growers. Okay, so we get these crystals, and then we go ahead and make devices. Okay, so we make devices on two types of flakes. One which is thick, more than 6 layers. This is something we don't like because of the fact that we have to be thin. I told you already less than 3 layers is what is our restriction. So we make devices on pristine material of MoSe2, right? And you can see that the pristine material is already kind of a little bit P, right? Because the Fermi level is mid gap, but you also see there is the pristine material is N, but there is a simple P branch, a little bit of P branch, which is not there for MoS2. Okay? So pristine material is N type, but once I dope it, something quite interesting happens over here. You see that with niobium doping, tantalum doping, and vanadium doping, these are now P type. I mean, you guys understand what is N type and P type, right? Right? Because now you have this branch of the current. Okay? But you see the bulk layers, which are thicker, right? I cannot have any gating. The gate control does not happen for a degenerately doped material. And this is what I was talking about. If I have a metal, can I change the conductivity of metal by applying a gate voltage? Why not? Very good, concentration is high, but why can't I change it by a gate bias? This is a very fundamental question. Let's first see whether you guys understand that why can't I use a degenerately doped channel, right? So our semiconductor structure, there is my pen here. No, band gap is there. No, not metal. I am talking about a degenerately doped semiconductor, right? So this is our semiconductor structure, right? Source, drain, and then I have this channel, source, drain, right? And this channel is something we want it to be a semiconductor, right? And this has, there is a gate. So there is some oxide, and then there is a gate. And what I want to do is I want to change the conductivity of this by applying a gate voltage. Okay? So what prevents me from having a degenerate, because we understood that if it's a degenerately doped semiconductor, throughout I will get the best contact resistance, correct? So why can't I keep this degenerately doped semiconductor in the middle? What prevents me? If I can control the conductivity of the channel by gate, why not have it? नहीं, ऊपर तो नहीं जा पाएगा क्योंकि यहाँ पे तो ऑक्साइड है, राइट? ये तो इंसुलेटर है, ऊपर तो नहीं जा पाएगा. Yeah, conduction band. Why cannot I control it? Why cannot I control it? Yes. Why cannot I control it? Yeah, you are on the right path. So what does the gate do? So when you apply a gate voltage over here, okay, it either inverts the channel or depletes it, correct? So it kind of puts some charges over here, right? Opposite polarity charges go over there. This is a capacitor. Remember parallel plate capacitors? You put charge on one side, it gets mirrored on the other. And by applying different gate voltage, I put different amount of charge, and that kind of negates whatever charge I have in the channel, right? And the amount of charge I can produce is this, Cox times Vg. Let's put it very simply, right? Because you remember, what is the amount of charge that a capacitor holds? Q is equals to C times V, right? So in this case, whatever the channel charge I can provide will be Cox times Vg. So far so good, right? So the maximum charge I can deplete, take it away or put it into the channel is this amount, okay? Now let's do a simple math, okay? When I have a degenerately doped channel, do you have an idea about what is the carrier concentration? Because at the end of the day, when I'm talking about a metal versus a semiconductor, it's all about how many carriers I have, free carriers I have, right? Any idea about the carrier concentration? I can tell you that number. You may not know on the top of your head. It is generally of the order of 10 to the power 15 per centimeter square. Okay, it could be even higher. So this is something we call degenerate doping, correct? So this much amount of charge is already there in the channel, and the channel conducts. So if I want to turn it off, I need to get rid of these charges, right? Because this transistor is right now on, right? Because there's a lot of carriers. If I want to make it a transistor, I have to be able to switch it off, right? So I need to be able to make sure that my gate can provide equal amount of opposite charges, right? Okay. So this is the amount of charge the gate has to reverse. Now let's do the math. Remember, what is the typical oxide thickness we are targeting? Remember from the first lecture, we spoke about, it has to be thin, it has to be high K, right? And we are targeting an EOT of, right? So let's see EOT is equals to 1 nanometer. Can I calculate my Cox? Can you guys calculate this Cox? Epsilon naught over epsilon 0 over, because 1 nanometer EOT means it is as good of a 1 nanometer thin silicon dioxide, correct? So epsilon of SiO2 by this Tox or the EOT, let's put the EOT, correct? This part is all good. So what is epsilon 0? Anybody remembers? Okay, let's take 10 to the power minus 11, correct? Epsilon, let's take 4 by 1 nanometer, 10 to the power minus 9. Everybody can see this? You guys can see in the bottom of the board? Okay. So that comes out to be 4 times 10 to the power minus 2 unit farad per meter square. Why? Because the unit of this is farad per meter. The dielectric epsilon 0 is farad per meter by meter, farad per meter square. Okay, so this is your Cox, correct? Across a 1 nanometer oxide, what gate voltage do you think you can apply? Can you apply 10 volts? Can you apply 100 volts? Why? Why cannot? Because oxides also have a breakdown electric field. Above a certain voltage or electric field, it will break down, right? You cannot apply 100 volt to a 1 nanometer, but you can apply 100 volt to a 100 nanometer. There is a breakdown field, right? So the material will simply break down. So the maximum you can apply is generally a volt, right? 1 volt for an EOT of 1 nanometer. So then what is the charge? 4 times 10 to the power minus 2 into 1. So this unit, yeah, Coulomb per meter square. This is the charge, correct? Now I have to find out the number of charge. What is the number of charge then? What will be my N? No, simply divide by electronic charge, right? So I have to divide this by 10 to the power minus 19, 1.6 I am taking away, right? So what is the amount of charge I should get? 4 times 10 to the power 17 per meter square. What will be it per centimeter? That's what I am talking about, right? 10 to the power 13 per centimeter square. So the gate can only deplete by this much. He is almost taking a spoon of water out of an ocean, correct? That's why you see the gate cannot turn the device off completely. Even after applying, this is not like a 1 nanometer EOT, this is a thicker oxide, right? I cannot. That's why I cannot use a degenerately doped semiconductor in the channel. Clear? But I have to use a degenerately doped semiconductor over here. Difficult problem. How do we resolve it? Okay, so now what we found is quite interesting actually. These are real experimental data. We found that for thicker layers, okay, it is degenerately doped, okay? But when you go to thin layers, it is not, right? It's a nice P-type characteristics. You see, right? There I can turn it off because here the current is 10 to the power minus 12, very low. The on-off ratio is almost 10 to the power 7. So this is a transistor. This is not. Okay? That's quite interesting. It's the same crystal. I have doped it same amount. When I go to a thin device, I can turn it off. A thick device, I cannot turn it off. Correct? So then, and this was also shown for tungsten selenide, right? Both the materials which are good candidates for P-type, we see the same effect. Okay? And you can also see that the niobium is a little bit better compared to tantalum. So there is some dependence on which dopant you choose. Okay? We'll come to that. Now, if I wanted to summarize this result, you can see that a transistor, a good transistor is one which should have a very high on-state current, right? Because higher the on-state current, faster is the transistor. At the same time, it has to be a good switch. So it should have a low off current, right? So your on-off ratio should be large, correct? So a good transistor should be something where the on current is high and on-off ratio is also high. So this corner is the desired corner, correct? That will make me a good transistor. But you see what happens is if I took thick flakes, they are here. They give high on current because the contact resistance is very low, but I cannot turn them off. Thin layers, I don't get good contact resistance, but I can turn them off, right? So now this is like a train, na ghar ka na ghat ka ho gaya, right? And it is independent of whichever dopant I choose. I could choose niobium, vanadium, tantalum, all the possible p-type we have exhausted, but still did not arrive in a solution.
So we have to make trade-off.
Yeah, because you need both. You need both. You have to be in this corner. And you're not being able to achieve it, so what should we do? At this point, what should we do? Okay? And after finding this, we actually came out with an idea to resolve it. Okay? So think about what we can do. Okay, I will guide you through this. But first, also quickly look into why is a thicker layer, because it's the same doping, right? Doping concentration is the same. So why is a thin layer, non-degenerately doped, and why is a thick layer degenerately doped? That's the first question we need to answer, right? So we did some DFT calculations. Okay? This is exactly where DFT helps actually. Once you know the answer, you go and ask the DFT folks, not to offend you. You do DFT calculation? Oh, you don't do DFT calculation, then I am safe, okay? Because whatever we find experimentally, they can explain. Right, so we say it, oh, camera is going on, so I will not say that statement, later we'll talk about that, okay? So what we are seeing is that, mono layer has a larger band gap, okay, compared to, the bulk layer. So whenever you introduce dopant into a system, there is a dopant activation level, right? And that is generally near the conduction band, and from which the dopant gets activated into the conduction band. And if you introduce hole type dopant, there is an activation energy level. Okay? And the activation energy level has a relative position to the conduction and valence band. So for a larger band gap material, it is more difficult to activate the carriers into the conduction or valence band. Okay? Even if you don't understand, don't worry about it, okay? But it is just that, there is an explanation also why a thick layer shows degenerate doping, while a thin layer is not degenerately doped, okay? And it comes from the fact that, the band gaps are different, and therefore the position of the Fermi level with the valence band changes for the different layers. You see, and the DFT calculation simply says that all are degenerately doped. That's not the case experimentally, but the trend is correct, okay? This part, no problem, right? So far, so good. Okay, but our question still remains, right? How do we get to a good p-type transistor? Okay. First, let me show you that if I go ahead and make a device on a thick flake, right? I should be able to get, according to our previous hypothesis, very low contact resistance. May not be very good off state, but very low contact resistance. So we go and make this TLM structure I told you, right? From the TLM structures only we can extract the contact resistance. So you kind of measure these devices, you make this plot, remember, total resistance versus channel length, and the intercept gives you the contact resistance, just the last lecture, right? So we can extract the contact resistance, and then we can plot it for different devices, okay? And you see that the contact resistance could be pretty low. For niobium contact, we are getting to 95, right? Our target is still 50. But we are strikingly close to our target, right? So niobium contacted degenerately doped contacts could actually work for p-type FET. That is established over here, right? Niobium is a good dopant. The next good one is probably tantalum, getting down to 180. Okay? So possible to get to very low contact resistance. That is solved. But then I have to now enable this, electrostatic control, right? So now, if you have to think about a transistor structure, One, which one? These are like 4 different devices with decreasing flake thickness. So this is just gone, in the bottom. That's why you cannot see it. So what we found is that as the thickness becomes, thinner, the contact resistance increases. Why? Because the doping efficiency goes down, right? So only for very thick device, my contact resistance is low because they are degenerately doped. That's what it is, right? So far so good, right? So therefore, if I think about envisioning a device structure which will give me both, shouldn't it look like this? What I should have is a thicker contact material which is thick under the contact, because then it will be degenerately doped, right? Well, the channel should be thin because that will give me gate control, right? So that way we can achieve the best of both worlds. This part is clear for most of you. If you have any question, ask me, right? Yes. So we just established that a thick layer gives me the best contact resistance, but a thin layer gives me the best gating, and I need both in a transistor. So I have to, and I know that I don't need to keep my entire channel thick, because then I will lose the gate control. So I need to make sure my channel is thin so that I have the gate control, while my contact resistance has to be reduced, so this has to be thick, right? So this is a device structure that is very similar to your silicon, because remember, in silicon, what structure do we use for? There's a P plus, there is N, there is P plus. Remember, this is the typical silicon device, source drain, heavily doped, right? The channel could be intrinsic as well, right? And this is something we could achieve, but now not through substitutional doping as such, but by designing the geometry, making the contact thick, because thick will remain degenerate, and making the channel thin, because then that will be non-degenerately doped. Correct? We just have to innovate, right? This is pure innovation that we came up with, right? This is not a structure that is used in the industry for silicon, right? But based on the observation, right? We did not expect that thick layers will be degenerately doped and thin layers will be non-degenerately doped. This was an experimental finding. Based on that finding, we came up with structure. That's why I'm saying, when you do experiments, you have to look out what the experiment is telling you rather than what you are trying to observe. Because often in experiment, what happens, you are looking for a certain goal, and if you don't get that goal, you discard that result, move on to the next experiment, right? Never do that. Okay, experiment always tells you something, right? Based on those experimental results, then you redesign your strategies. Correct? This is literally what we did over here, right? Now you do that. Now the question is, how do we create this structure? I want this, but how do I create it? Yes, tell me.
You can create a first of all FET, multi-layer FET,
Mm-hmm.
and then etching or some
Yes,
plasma etching or
that's very true. You have to etch it. But now the problem is, you are trying to etch a single layer. Yeah, I mean, how are you going to etch one and stop at the other one? Right? This is experimental challenges. How do you controllably etch one by one layer? This is again 2D materials comes to rescue. Okay? Amazing property of the 2D material allows us to do something called atomic layer etching. You can etch layer by layer. Okay? So what we do is, we start with this multi-layer flakes. Okay? All 3 layers are there. Oxygen plasma. This oxygen plasma converts only the top layer into tungsten oxide or moly oxide. Okay? And it stops there. You can keep doing the plasma for long. It will not go and affect this guy. Okay? It's self-limiting. It's a self-limiting oxidation process. Okay? It just stops over there, because you see that the oxygen atoms cannot penetrate through. And if these layers don't see the oxygen, they cannot get oxidized. This is very different compared to a conventional 3D material. Okay? So what happens is, you can actually thin it down. And here are some evidences. You take a flake. So you do an oxygen plasma. You convert this top layer into moly oxide. Okay? And this moly oxide is soluble in water. Okay? So you etch one layer, put it in water, one layer gone. You again put oxygen plasma, put it in water, another layer gone. This is called atomic layer etching. Here is the evidence. You see the AFM images? Every time we etch, it gets thinned down by one layer. Last one is everything gone. This is one layer. Correct? So we have even the precision of etching atomic layer by layer. Okay. Once you do that, so we kind of do the plasma for every 15 seconds, and then we dip it in water. Another 15 seconds, dip it in water, and you just etch it layer by layer. Yeah. Yeah. This is the height profile going down layer by layer. Right? Full engineering. Metal contacts is already there. Metal contacts are already there. No, 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 no. This is a mild oxygen plasma. And these metals are like, we are using palladium, gold. They don't oxidize. They don't oxidize. Right? And many metal oxides are also conductive. You see, and you can always, also protect the metal layers and then do the etching one by one. Right? And that's what we are doing actually in this case. So, okay? So we can now create this structure. Okay? That is why, plasma etching is always good. This is reactive ion etching, very directed, very anisotropic, right? So if you do wet chemical etching, that is more anisotropic in nature, right? So plasma is good. I mean, of course, there is some penetration over this direction, but that is actually minuscule. We have done both calculation, and I'm going to show you something that will make you believe that we can actually create this structure. Here, this is a cross-sectional TEM. Okay, here is the contact, here is the channel. Count the number of layers here. Count the number of layers here. Right? I was fascinated after looking at this TEM image because even I did not expect that it will work so well, that we could literally, layer by layer thin it down, and now see what happened. This device initially I could not turn it off. Now I could turn it off, and I did not lose too much on the on current. Right? Kind of achieve, best of both worlds in this case. Right? So this is where I love experiments. I mean, there is no much fun or better feeling when you kind of see this kind of images. I mean, it's too good. I mean, this TEM image, and we have an excellent expert at Penn State. We have a faculty with whom we collaborate. We don't do TEM ourselves, but yeah. And yes, that's what I'm saying. Sample preparation after everything, you can literally three layers versus 6 layers is incredible. This is incredible. I mean, people who do TEM, they will immediately appreciate this figure so much. And we appreciated it because we thought this is happening, right? But we could never kind of convince ourselves until we see this image. Yeah, that is really going layer by layer. We did it 3 times and 3 layers were gone, right? I mean, this was magic, literally. Okay? Which one? So this is high angle annular diffraction pattern that we are taking. So these are like different way of doing the TEM. This is just on a high angle. Okay, good. And then we also did more engineering. We thought not put only one gate, which is in the bottom. Why don't we go ahead and put a gate on the top? Okay, that will give us even better performance. Now you see 6 layers, 3 layers, and there's also a top gate, right? And look at the channel length of this device, right? Only 50 nanometers. Is there competing with the most advanced silicon technology out there today? Right? So these are really engineering feats, I mean, that we could have achieved. We have a patent, yes. We have a patent for this. And then we kind of did all the measurements. Now we could get to very high on current numbers, 200 microns per micrometer, good on-off ratio. So we could have achieved, best of both worlds. There is a benchmarking table, and we published it in Nature Electronics actually, just a few months. Oh, it just, yes, last month. This is in the issue last month. We published it in Nature Electronics. It was reviewed in Nature as well, but Nature has too high of an expectation. But we could eventually publish in Nature Electronics. Then we started doing it over large area, because what I showed you was for crystals. And we started seeing very similar effect, with large area grown, niobium doped, because now you can think about growing a large area film with the dopants, but not monolayer, thicker layers, and then thin it down. We could do the same thing actually. You see, as I go from a thin layer to thick layer with niobium doping, I get from ambipolar to P. Right? Because we first proved the hypothesis and the principle how to do it, now the way to scale it up. So now we are trying to scale it up because we cannot work with flakes when we are trying to make a billion transistors. Right? This is the ultimate approach that we have to take. You have a question? Yes. We did it 3 times because the initial starting layer was 6. In experiment, it is not that we planned to do it 3 times. What we did is that we even did not know what is the starting thickness. We made the device, measured it, then I asked the student go and do the oxygen plasma 1. Every time he has to go gown up, do the plasma treatment, come back. He came back, we measured, nothing changed. Go again. You see, that's the good part of being a PI. I don't have to do it. Student is there, he's going and doing it, right? He goes, does it again, coming back, little bit of change, go do 1 more time, right? And then we stopped when we realized that, okay, this is the perfect curve that we are looking for, right? And then we did not do afterwards. So the experiment is also trial and error. It is not that it goes according to your plan. So, and this is why exactly you need a lot of hardworking, motivated students, right? After 2 times you said, oh sir, nothing is happening. Do it the 3rd time, do it the 4th time. Do not stop. Do not stop, right? That's important. So this is what, is one story of getting a good or high performance P-type FET, right? Now there are also other works that we have done. They are not as exciting, but this is more recent work. We have also tried to now, because at the end of the day, it is just not the doping, but also controlling the doping percentage, right? So when you're doing large area, now we have started looking into, can we actually create different doping percentage? That will give me a little bit more control over the channel, right? Because otherwise it is arbitrary doping. And when I make a device for circuits application actually, I need the right threshold voltage. I cannot work with any threshold voltage. So we can have started now looking into different doping percentage and how can I tune the properties by that. Okay. And as I told you that there are different ways of doping. What we spoke about so far is the substitutional doping. We were literally putting the atoms inside the material, right? You could also do something called surface charge transfer doping, which is a remote doping. This is also something only possible for mostly 2D material, where you don't have to go and change the atoms inside the 2D material, but you put something close to it and it does a charge transfer. Okay, that is called surface charge transfer doping because our 2D material is nothing but a surface, right? I could do that for 2D, I cannot do it for silicon because silicon is bulk. If I put it something on the surface, something will happen close to the surface but nothing underneath. But the 2D surface charge transfer doping could also happen, and we have actually looked into many different ways of surface charge transfer doping, a lot of things. But one thing which was interesting, this was our older work actually. That time we did not engineer this doping and stuff. We found that moly oxide is actually a P-type dopant for the underlying moly sulfide. Okay, and when you oxygen plasma it, you don't get a very good, because we just spoke that MOS2 can never be P-type material. But we found that when you convert the top layer into moly oxide, that dopes the underlying material into P-type. So I will just show you some characteristics. You see, as I keep doping, some P branches show up. Okay, but the P branches are not very good. You see only a microamp current, and we were achieving 200 microamp for tungsten selenide, right? So even though we can do surface charge transfer doping, it's not the best approach for MOS2. Okay, we can only get so much of good P-type characteristics. This is an older paper, 2020, and what I showed you earlier was more recent, right? But I just want to tell you that there are alternative ways of getting, P-type the material. We are trying to do a lot of these, this is a more recent paper where we have also studied the impact of this oxygen plasma, right? Because there's a lot of aspects associated with this oxygen plasma. What is the optimum time of doing this oxygen plasma? More recently, okay, we forgot about this structure. This structure is the ultimate structure. What we spoke about at the beginning is the ultimate structure. Okay, no doubt. But we also found that nitric oxide is an amazing dopant for my 2D material. Okay, and we have been able to report the record high performing device. Let me see. I will not go into the detail of this. So here you see this is our characteristic. This is not published. Okay, this is under revision. We are going to get it out very soon, within a month. I'm traveling, and that's why my students are not very happy, because I'm not being able to revise their manuscripts. so this is going to come out mostly within 2 months. So we have been able to demonstrate the best performing FET so far. Okay, you can see where is our work over here. There is a Purdue work over there, but the target corner they have not been able to achieve. And we are comparing it with all the existing results, including results from IMEC, TSMC, Intel. Okay, so we are not competing with other universities. Okay, the competition is straight on with the industry. Okay, and we are able to get to very high performing devices. So, specifically, this is the one I was talking about: high on current as well as high on off ratio. Right, that was our main objective, and see with NO doping where we are compared to rest of these. Right, so P-type FET also appears that we are close to solving the problem. Okay. Yeah, of course. I told you right in the first lecture that Intel, IMEC, TSMC, everyone, right? So the competition is very tough. You see, we are head on with these industries, which have almost 100 times more resources than what we have, right? That we could still compete with them. And here is a benchmarking table. Again, we love putting this benchmarking table because this provides the the readers a very good platform to compare where we are in terms of what have been happening in the literature. So it's too involved. Don't worry too much about it. But I think the take-home message from this lecture is that contact resistance for P-type 2D FET still remains high. Okay, although we have achieved it not 50 ohm micrometer, which was achieved for MOS2 for NFET, but the PFET it is still high. Okay, it's of the order of hundreds of ohm micrometer. We still have a longer way to go. But palladium and platinum are promising contacts with degenerately doped channels. Not only high work function metal, because for MOS2 we found that only low work function metal does the trick. For P-type, we need both a high work function metal to reduce the Schottky barrier, and then degenerate doping to reduce the Schottky barrier width. For MOS2, we did not need that. So for WSE2, we need both. That's why doping becomes even more critical for P-type materials, right? And for growers, right, you should be focusing on this aspect, right? And both substitutional and surface charge transfer doping could be viable alternatives to achieve this objective, but it's still an open field. Okay, it is closing, the doors are closing, and our tough competition is also with another country, our neighbors. Okay, not on the western side. Okay, of course. Okay, with that, I will conclude this lecture. I will take any questions, and then we'll move on to the next topic if we have time. Yeah.
Compared to vanadium and platinum, it has more high on-off ratio. What's the reason?
I think it's not about the on-off ratio. If I go back to this slide you're talking about, right? So niobium is actually the best in terms of the contact resistance. You see, it's the lowest contact resistance. Now, one thing I have not mentioned in this slide is that not that each of these dopants have this similar amount of doping. Okay, because we did the CVT growth, and you never knew that whether niobium was 100% activated versus vanadium is 90% activated. We do not have an idea on that. So very beginning, I showed another slide which was too much, and I did not discuss it. We have done some of these characterization called ICP in order to find out what is the dopant concentration. You can kind of see the niobium doping percentage is higher, right, compared to the tantalum one and compared to the vanadium one. But this still does not tell me what is the activation. Just because there are more dopant present doesn't mean that all of them are activated. And that we have no clue about. It's very difficult to find that out. And when the doping concentration is so low, even in cross-sectional TM, we will not find it open. You know, you are just literally trying to find a, you know, hair in a big room under dark, right? So it's very difficult to find out the exact concentration. So therefore, we only know qualitatively that once you put a lot of these niobium, vanadium, and tantalum, I get to degenerate doping in thicker layers, and that's why, you know, later part, you know, the point I was trying to make is that we understand that niobium, vanadium, tantalum are good dopant, and this is the way to go, because here I can start controlling the doping percentage, right? This is why this came, that I can now controllably do 0.6%, 0.9%, 1.9%. So control we need to engineer eventually. Conceptually we proved that thicker layer, degenerate doping, thinner layer, non-degenerate doping is needed. But now we need control. We need control, we need scaling. Scaling will come from CVD growth, and control will come from controlling the doping percentage. Right? Both the saying that, you know, we have shown preliminary work, a lot of work remains in the field right now. And this is a very good opportunity for, again, you know, the people who are getting into PhD programs. Did I answer your question to some extent? Yeah, we can have more discussion, no problem. Other questions?